Hello, everyone. My name is Chengcheng Liu, and I'm from the AIGT team at the China Innovation Center of Roche. It's my great pleasure to introduce an R Shiny App we developed for tumor-normal expression analysis. So I don't know how many of our audiences are from early R&D, but I guess we will all agree that tissue-specific expression profile is really critical in cancer drug discovery. We need it for target ID and validation, for biological insights, safety profiles, biomarkers, and indications, and the design of clinical trials. And for bioinformaticians, I guess the most well-known expression databases should be GTEx and TCGA. So GTEx is an encyclopedia of normal tissues with 17,000 normal samples and of 54 tissue types. And TCGA pan-cancer is the most comprehensive cancer dataset with 11,000 samples of 33 cancer types, and also a few hundred adjacent normal samples. However, these samples are highly heterogeneous, making it difficult for a direct comparison. There has been an effort by UCSC called the XENA dataset that recomputed and normalized all samples from raw counts to allow expression comparison and minimizing batch effects. Also, there are many public tools for expression analysis, and the most popular one is probably GEPIA, developed by Professor Zemin Zhang's lab in Peking University. So they published 2 articles, both got thousands of citations, and here are the example outputs by GEPIA for the expression of a given gene. So we can see the dot plot, the bar plot, the heat map, the box plot, and the 2-gene correlation plot. But meanwhile, there are some needs that GEPIA and other tools do not support. So here are some real example requests we got from our scientists, like I like more plot types, more customized, I need the fold change, what is the safety window, what cancer type has the most overexpression, and please help me pull out the data. So this is the rationale we developed this shiny tool called TNfinder. The main feature of this tool is that it provides fast and flexible tumor-to-normal expression analysis, helping the scientists to freely explore cutoffs, patterns, patient distributions, and cancer markers. And this is how the web interface looks like, but I'll skip it for now and have a live demo later. So first of all, it provides a visualization of expression pattern across tissue types. So here we chose a violin plot to better reflect the distribution. And we also have a heat map to show the clustering of expression patterns across tissue types. And I also want to highlight here the flexible plot options such as size, orientation, text, labels, orders, etc. They all can be adjusted. And in addition, this tool can calculate tumor-to-normal fold change and provides a bar plot of fold change across all tissue types, and also a dot plot showing each gene in a row. Yeah, it allows multiple gene inputs, and the color represents the fold change, and the dot size represent the expression level. So this actually allows us to do a cross-tissue comparison and indication prioritization. And next one, this is a pretty unique feature, and we call it cutoff finder. It helps scientists to explore cutoff for overexpression using different criteria. So whether you would like to get the max separation between T and N, or if you expect proportional samples in either group, or you want to use any custom value, you can visualize them in an interactive graph. So for example, I want the overexpression in normal to be 1%. So I put 1 here, and then it does the calculation for me and tells me the cutoff should be 3.7 in log 2 TPM scale. And the corresponding percentage in tumor is 85.6%. So here we can visualize the safety window. And next, it also gives you a bar plot of overexpression percentage by tissue types based on the cutoff you use. And the next feature is called Marker Finder. This one allows user to explore tissue and tumor-specific marker genes. So here is an example case. If you are interested in stomach, so we select stomach, and we want a surface protein that is high in cancer and low in normal. So I give it a few numbers, and then I'll get an interactive graph showing genes that pass all those criteria. And x-axis is tissue specificity, and y-axis is tumor-to-normal specificity, which are both estimated by Gini coefficient. So we can see the gene to the right. This one is our top stomach surface marker. Of course, it's Claudin 18. And then we can click on it to see its expression profile. And the next feature, this one is a new one, so it's still in development. This one is to visualize the co-expression pattern of two genes. So on this page, we could select two genes and get a scatter plot and a distribution curve. So here we apply a different method, the Gaussian mixture model, to determine the cutoffs. So this works especially well for genes with bimodal distribution, and this one is an example. And on the right, it gives us the 2x2 table with number and percentage of samples using the cutoffs. And finally, it allows user to download the tissue level statistics, the gene level data, and the sample level data files. So there are 2 minutes left, so I'm gonna show a short demo. So if you can see this, this is the interface, and here we can choose a single gene or choose multiple genes. So it can recognize the gene name and let me know if the gene name is not found. And on the right, we can select tissues, and it can also show the number of tissues and samples we just selected. And below it, here is the parameter panel. So there are many choices like the order, median quartile, significance, sample size, orientation, highlighting selected tissues, legend position, and also a custom cutoff. I'll come back to it later. So I'll show, let's say we enter a gene and select all tissues and run. So it takes several seconds to display all graphs. So here is a violin plot and the interactive heat map, the fold change. Of course, we can also choose to order by fold change. This one looks better from high to low. And here is the dot plot of fold change. Okay, and next we come to the cutoff finder part. So for faster speed, I'll reduce the number of samples. I'll choose GI tissues only. And here, by the way, I can show how we can adjust graph size and other steps quite easily. And going down here, so yeah, I'll show the interactive mode of the cutoff finder feature. I click this one. Here it is. You can move your mouse around to see the percentage of samples at different cutoffs. And there are also some predefined values, and you can either choose different cutoffs, or you can even click on the graph to get the click value, like here. So let's say I just want this one, and I go up, go back to the cutoff value selection, and I put in the number, and you'll see there is a new cutoff line showing here. And here there's a new graph showing the percentage of patients with overexpression using the cutoff you just entered. And
sorry, we're at
finally,
time there.
Yeah, sorry, lastly, here are the tables, and you can choose to download everything. And also the marker finder, the co-expression, I'm not going to show them today, but we also have a data source and documents. So lastly, going back to the last slide, we developed a Shiny tool to deliver gene expression analysis to complement the existing tools. We are still working on it, and there are more features coming through, but we will make it open source very soon. So that's all for my sharing today. Thank you.
If no one else does, I had one. So showing expression data when you change the number of filters, one thing I've always found to be very slow doing that is having to do renormalization based on the subset. Is that something that you skip here, or is that all pre-calculated?
Which one? Sorry.
So when you change the number of samples, do you do renormalization?
No, it doesn't do the renormalization. Yeah, they're all pre-calculated, but because the data set is pretty large, so it took some time to retrieve those data and do the subsetting and all the other filters.
Okay, I don't think there's any other questions in the chat. So once again, thank you, Chengcheng. We'll see you all after the break.
Thank you very much. Bye-bye.